Hello, my name is Jason Smith. I'm with the Georgia Tech Center for Music Technology with advisor Jason Freeman, and I'm here to present the effects of deep neural networks on the perceived creative autonomy of a generative musical system. The rise of deep learning has led to the creation of collaborative agents and collaborative systems, artificial intelligence applications designed to create something alongside a user. Creative autonomy is the ability of a collaborative system to display independent decision-making in the creative process. Artificial intelligence agents, when used in the domain of music, can act as tools used by a user, displaying little autonomy, or as autonomous actors, which follow their own directive and create concurrently with the user. This work aims to explore both paradigms by analyzing the relationship between a user's perception of a model's strength and that model's role in the creative process. This work aims to answer two research questions. To what extent can the inclusion of a deep neural network in a generative musical system affect its user's perception of it as a collaborative agent that exhibits creative autonomy rather than an instrument responding to their controls? And how does this compare to a shallower neural network in the same system? And to what extent does a user's perception of the musical system's creative autonomy affect the level of control the user retains and gives up in the creative process, as well as on the user's self-reported expressive ability with the system? To answer these questions, we have created a simple generative music system that hosts a series of neural networks. In the training mode of the system, users perform gestures while manually setting 6 sliders. These are gain, center frequency, and resonance for 2 bandpass filters, which act on 2 ambient signals continuously playing while the application is running. In the testing mode of the system, users perform gestures as the model generates the filter parameters it has learned from the user's gestures while training and applies them to the signals. Depending on the model used, the background color is changed as well. This system was designed with 2 neural networks, both developed in PyTorch. These networks take an 8x8 input image, constructed from a downsampled image created from frame difference from a computer's webcam, representing the current motion at that time. A shallow network, containing a single linear layer, as well as a deeper, albeit simple, convolutional network containing 2 convolutional and 2 linear layers, were trained by repeating a series of motions while varying a set of audio parameters to match. As series of frames differences were collected alongside stored filter parameter settings, collections of gestural motions alongside large-scale changes in filter parameters were used to form a dataset used in training our models. Through 17 data collection sessions, with an average length of 46 seconds, a dataset of 9,423 samples, pairs of 8x8 arrays of camera frame differences, and 1x6 arrays of audio parameters was created. 70% of these samples were used for model training, with the other 30% reserved for validation. This data generation and training was performed during the development of the system and before the user studies began. A convolutional neural network was used instead of a more robust sequential model for the following reasons. Both a shallow linear model and a convolutional model take a single frame difference as input, as opposed to a series of frame differences as with a sequential model. The convolutional model also performed similarly in training loss, training time to the shallow model, and had an identical data pipeline. We will now show a short demo of the generative music system in its testing mode, both using the shallow neural network and the deep neural network. We designed an experiment to compare users' perceptions of the system outfitted with both models. First, in a pre-questionnaire, subjects were asked to indicate their musical preferences across 15 genres, the scales for input of the short test of music preferences. These were later used to evaluate how their performances with the various versions of the system conformed to their musical tastes. Next, subjects rated their experience and interest in both music, including live electronic music with and without collaborative AI systems, and machine learning and deep learning. Following the questionnaire, subjects performed a guided performance task using the software. They alternated between two versions of the system in a random order for 2 5-minute practice sessions and 2 2-minute performances. They were encouraged to think aloud during the practice sessions and to explore a musical idea during the performance. Following the performances, subjects watched the recorded videos of their 2 performances. For each, they identified between 4 and 8 notable musical interactions and rated their interaction with the system on 2 7-point scales. Autonomy, how well the system felt like an independent agent rather than an instrument, and control, whether or not the system influenced the current musical state. Additionally, they rated the musical output of both versions of the system on the output scales of the short test of music preferences to see if one model more closely matched the results from their preference test in the pre-questionnaire. They also rated each model on the scales of the Creativity Support Index, comparing the two. These ratings were collaboration, enjoyment, expression, wanting to use the system again, and whether or not the system performed at a high standard of musical output, and how well the output resembled that of a human performer. Finally, users answered interview questions about how the system affected their musical goals during the performance, if the experience changed their interest in working with AI musically, and any other design feedback they had available. Among our 5 subjects, all of them Georgia Tech Music Tech graduate students, we found an increase in collaboration, enjoyment, expression, and willingness to use again for the deeper model, on average. Notably, the ratings related to musical contents of the system's outputs were identical. 3 of the 5 subjects reported that the deep neural network version felt more responsive than the shallow version. Additionally, one subject stated that both versions brought them through the narrative of working it with an instrument before a partner, but it was faster with the blue one. One subject, Subject C, who reported a strong preference for the deeper model in terms of expressive ability, felt that they had more control with the more autonomous model. They stated that they gradually began to acclimate to the model's output, learning to regard it as a collaborator, and came to exhibit a different kind of control than they had previously with a traditional instrument. As a contrary example, Subject A, who preferred the shallow model, had a specific compositional goal in mind when using the system. They stated that the black box nature of the system impeded their ability to execute that goal, and as such felt more comfortable and expressive with the shallow system's predictable output. The results of this study suggest a relationship between the presence of a deeper model architecture in a system and the perceptions users have for that system's exhibition of autonomy, control, and musical expression. Despite using identical audio samples and filters, the deep model outperformed the shallow model in user ratings for creative autonomy and control in its musical interactions. Despite this increase, as well as the increase in expression and collaboration as rated by subjects, a significant link between control, autonomy, and expression was not found directly in this small subject group. However, this perceived autonomy is dependent on the user's creative goals, and a lack of understanding the model's inner workings can diminish a user's sense of that system's expression. Subjects initially reported high interest in performing using a collaborative agent, averaging 6.2 out of 7 in their pre-survey questionnaires. When asked if this experience affected their interest, all subjects either responded that it had stayed the same or increased. For example, Subject E stated that they were still interested in collaborating with AI, but would need to know more details about the model's performance before doing so. They stated that it would affect their relationship with the app. Given time learning the mappings of a system, they would be able to teach themselves a series of gestures to perform machine-led parameter changes. Another Subject D stated that they would want to know the nature of the collaboration, as this experiment used once the controller using gestures while the system generated audio, and as such didn't feel truly back and forth as a mutual collaboration. Lastly, subject B, who rated the deep version higher in both control and autonomy but not expressive ability, stated that they spent more time learning how to use the deeper model with less time to truly form a musical plan. As such, they would have appreciated to be given more instruction or visual indication in a future version of the system. Three limitations in this study were the use of a small group of subjects, all of whom had musical and computer science experience, and the lack of a model-less testing condition or randomization of the background color. Although partially due to COVID-19 related logistical issues, we plan on expanding and diversifying our subject pool in future work, as well as replacing color randomization with other methods of visual information. Other areas for future work are to expand the system to generate full audio, enabling more compositional ideas from users, as well as studying the effect of model interpretability or explainability through visual communication. Thank you.